Yes, I am a Sierra postdoc fellow. Very happy to be spending the month of February away from Chicago and in California and enjoying this program. So thank you for having me. And I'm going to be talking about initial conditions. I'm just going to start with basically the conclusion, which is that I think we need to be very careful about what initial conditions we use for black hole accretion simulations if we want to study their outflows and also black hole formation. And Chris and I had a good conversation about this the other day, which is that, when we do these simulations, like initial value problems where we're solving equations, we want to either believe that the initial conditions don't matter to the steady state results that we get, or we want to really well understand what the initial conditions are. And I think that we are in neither of those regimes in this field. So that's what I've been thinking about. And in particular, I'm going to be talking about two different projects. The first part is about collapsars. So since this is a wide audience and people maybe do not think about stars often, except the sun, I'll start by introducing. So collapsars are a model for long duration gamma ray bursts. They're the favored model for these since 1999 when they were first proposed by Andrew McFadden and Stan Woosley. And basically, long duration gamma ray bursts, which have durations of a few seconds, are associated with massive stars. We sometimes see them coincident with supernovae, and so the thought is that they're related to massive star deaths. Collapsars also in recent years have drawn additional interest because they're suggested as a site of heavy element nucleosynthesis through the R process channel. So a paper in 2019 in Nature led by Daniel Siegel suggested that collapsars may even be the dominant source of R process elements in the universe. So these are elements like gold, platinum, europium that we know are made in neutron star mergers, but may also be made in these events. And the model is basically that you have a star, a massive star that's evolved. It likely has had some mass loss and been stripped of its stellar envelope. And at the end of its life, its iron core collapses under gravity, forms a black hole, and then this stellar envelope that has some angular momentum profile and some magnetic field accretes onto the black hole, perhaps forming an accretion disk. And that disk accretes through turbulence driven by the magnetorotational instability, or MRI, and may launch some R process enriched outflows in a disk wind and also drive a jet that is later observed as a long duration gamma ray burst. So this is the model. Actually simulating this entire process self-consistently is very hard, both numerically and physically, because of our lack of understanding of initial conditions. So on the numerical side, one of the main issues is severe scale separation. So if you want to resolve the whole star and the jet breaking out of the star, that's on order 10 to the 11 centimeters. And if you want to resolve processes happening at this very not to scale drawing near the black hole horizon, that's at about 10 kilometers. So you have a huge range there. And then also in duration, if you want to capture the jet being formed near the black hole horizon and then launched and propagating all the way through the star and breaking out of it. You also need to do this in full relativity with MHD because the processes for launching the jet depend on relativity and magnetic fields, and you want to capture that entire process. So we do this with Hammer, which is a GPU accelerated code written by Matthew Liska and collaborators that allows us to capture this entire scale separation and use AMR to resolve the jet all the way through. You also, if you want to study, especially the nucleosynthesis side of it, which is something I'm very interested in, need to have neutrino transport and microphysical equations of state. And that's being implemented by a student at Northwestern, Goni Halevi. So that will soon be possible to do that full problem with nucleosynthesis calculations as well. On the physical side, we need to prescribe some angular momentum profile to the stellar envelope, which is not well known because massive star evolution, especially for 3D properties like angular momentum and also their magnetic fields, are quite elusive to simulate from beginning to end. And then we also need to choose some stellar profile. So what is the density of the star? What is the pressure, temperature? And I have focused on that part partially because the stellar density profile is really what controls the rate of accretion onto the black hole. And that also controls the neutron richness of the material, we believe. So that'll affect whether you get these R process elements out of it. And it'll also affect the jet launching and propagation. So what has been done before by my collaborator, Or Gottlieb, is to take our favorite prescription, a power law for the density profile, and just vary these alpha and delta parameters. So in this case, delta controls basically how fast this stellar profile falls off, not so important, and alpha controls the slope of the power law in the region that we care about, which is where it'll start accreting onto the black hole that has a gravitational radius somewhere around here. And what you see in pink is this very commonly used stellar model for like long duration gamma ray burst progenitors. And it has a power law of about 2.5. But that turns out to give you a jet that is too powerful compared to observations of gamma ray bursts in order to have that jet break out of such a density profile. So what I did was use a bunch of updated stellar models where here you're seeing compactness parameter, which is a probe of how compact the core of a star is, versus its initial zero-age main sequence mass. And my collaborator, David Aguilera-Dena, made all these models. You see this very non-monotonic behavior in stars that is annoying for people that simulate core collapse. So I chose a bunch of different stars. I ran them through a 1D but dynamical general relativity code that includes neutrino transport to model their collapse all the way to black hole formation. So here you're seeing the time after the supernova or the core bounce and the central density of these stars, and you see some of them shoot up exponentially. That's the formation of a black hole, and those are going to be the stars that are likely collapse star progenitors. This is also showing the shock radius, so all of these have failed supernova explosions and turned back, and the ones that form black holes with masses about 2.5 and higher solar masses, which is dependent on the equation of Stately's. And what we find is ubiquitously, we start with a range of initial density profiles that all have about a slope of 2.5, like that common one, but once they actually form a black hole, those post-collapse density profiles are much shallower. They're closer to 1.5. So this is the only power law that you'll see in my talk, I'm sorry. No turbulence power laws. But it's kind of a fun one because the slope that you end up with is basically what you expect just from a simple free fall model, even though you've put neutrinos and dynamical GR into these collapse simulations, you just get free fall. And this slope is much more consistent with observed long duration gamma ray burst luminosities. So that's nice. So what we do is take and working with a student that I'd been advising at Princeton, Belinda Wu, added pressure to these simulations that were before artificially cold. And what we find is in very short times, you form a jet rapidly in an accretion disk. So on the top, you're seeing magnetization, and on the bottom, you're seeing density. So you form this low density, highly magnetized jet. This is for a star that has an artificially cold temperature. When we add more realistic pressure that's motivated by our 1D simulations, we find slight differences in the jet launching. So you have a slightly larger opening angle that translate into differences in jet propagation. So this is at early times, about 100 milliseconds. And you see on the left, this artificially colder star, on the right with the more realistic pressure. And there are some differences in how the jet is propagating through the star immediately. And as you evolve further in time, all the way to the point of jet breakout, which happens at about a second, you see that the jet in the warmer star travels more slowly through the star and breaks out at a later time as well. So these small changes to your prescriptions for initial conditions that are anyways not very well motivated can make a difference in your observed properties of the gamma ray burst jet that you would describe. So the main takeaway here from this part is that we can, with modern tools, GPU acceleration, something like Hammer, entirely simulate this collapsar process, capturing from the very small scales near the black hole all the way through to the largest scales of breakout from a stellar envelope. But that the initial conditions that we choose for these models affect the jet properties in ways that we haven't fully explored, and this requires us to be careful when making comparisons to observations, and also when we do the full nucleosynthesis calculations, which make this problem no longer scale-free, and you need to care about what the temperatures are when you have neutrinos and opacities and all the other microphysics. Okay, I'm going to move on to the second part. So I use the word dynamo here, but this is very much work in progress, so don't expect like detailed dynamo analysis from me. And in this context, what I'm interested is in primarily in mergers between black holes and neutron stars. So this is a type of black hole disrupting a star, but this is also relevant to tidal disruption events. And this is work done with Elias Most, who's new faculty at Caltech, and my PhD advisor, Jim Stone. So most simulations of accretion disks start with some hydrostatic equilibrium torus solution, these well-known analytic solutions, and then add a magnetic field on top of that, usually a large-scale colloidal field. But we know that certain physical systems, like binary neutron star mergers or black hole neutron star mergers, tidal disruption events by supermassive black holes, should really form disks that are dominated by a toroidal component. And this is just basically because you get largely toroidal magnetic field lines. So questions that are left and very well set up by Chris's previous talk. Do we have dynamo action actually occurring in these toroidally dominated accretion disks formed in mergers or disruption events? And if so, what is the nature of that dynamo process? And there are very nice papers that were already referenced as well by Chris, by Matthew Liska, and then analysis of that simulation presented by Matthew's paper by Jonathan, that look more in detail into what is happening in this idealized disk scenario, not specifically applied to disruptions, but just you start with a very thin disk that is toroidally, only threaded with toroidal flux. And then another question is specifically in the case of these disruptions and mergers, what does the long-term evolution of the disk look like, and what are its outflows? And in particular, do you get a relativistic jet from these events? And what are the properties of that jet? And there are two nice papers by Or Gottlieb looking at these two questions as well. So we know that some of these systems observationally have jets associated with them. In particular, mergers have short gamma ray bursts, recently also potentially long gamma ray bursts produced by them. And we see some subset of tidal disruption events that are jetted as well. And since this is a broad audience and nobody has formally introduced it, we think that in this case, jets likely are formed through the Blandford-Zanaik process, and that relies on having some vertical magnetic flux reaching the black hole horizon. So you have some vertical field line that's dragged into the horizon, a rotating black hole that winds up that field line, forming some magnetic pressure above the black hole polar axis. And then that pressure builds up until you accelerate material along the jet axis. So the question is, if you start with toroidal fields, can you actually generate the large-scale colloidal flux that is necessary to launch jets? And in order to explore this, we need to have relativistic models. So in this case, I use Athena K, which is a rewrite of the well-known Athena++ code that uses a library called Cocos to be portable to GPUs and be able to run higher resolution simulations than before. And I set up two different commonly used equilibrium solutions for disks. One of them is the Chakrabarty disk. And in my initialization, this is a thinner disk than the other one, which is the Fishbone-Moncrief torus. And they both are set up with the same inner and outer radii. So they have pressure maxima that are at a few tens of gravitational radii. And we add a purely toroidal field at first that has an average plasma beta of about 10. Resolution is hard for these types of simulations because if you want to resolve the MRI vertical modes, those require far fewer cells. So this, compared to azimuthal modes of the MRI, have a much more stringent requirement. So We use a Cartesian mesh, which is in opposition to what most other codes do that rely on spherical symmetry in these disk solutions. This is from Peyton's paper that Chris just talked about. And static mesh refinement. Sorry. Okay. So this is just showing you our initial setup with the grid overlaid. So that's the Fishbone-Moncrief torus, very thick torus, H over R of about 1. Here we're looking at it edge on and face on. Like Omer, obviously these are 3D simulations. And then we run it with twice the resolution just to confirm that we are converged on the key metrics that we're looking at. And you see that the Chakrabarty disk is significantly thinner, so it's harder to resolve and we're more marginal there, but still have a lot. This is, I think, the simulation that this stress is based on. But just to show you that this is a slice through the midplane, we have very high resolution and we have no obvious imprints of the Cartesian grid, which is nice and comforting because people have not done many disk simulations in Cartesian meshes before. Already have been introduced to the butterfly diagram, but for the sun people, you know, the origin of the butterfly diagram is from observations of the solar dynamo, where you see sunspots drifting towards the equator. And we see this dynamo in my disk simulation. So this is for the Chakrabarty disk, the thinner one. And you see a very nice evidence of this butterfly diagram happening here. Whereas for the Fishbone-Moncrief disk, it does not look so pretty. I would not really call this a butterfly diagram. And here we're plotting, just like Chris showed, the toroidal component of the magnetic field at a given radius, but averaged azimuthally over time. Okay, so I'm gonna show a couple movies of slices. So now you're viewing the disk edge on. And on the left, you'll see the Fishbone-Moncrief torus. On the right, the Chakrabarty one. And what we're showing is magnetization. So the light blue is highly magnetized material. And you will see that they evolve quite differently immediately. So the Fishbone-Moncrief torus quickly accretes and has outflows that fill the volume of our domain, whereas the Chakrabarty torus evolves much more slowly, launches some sort of weakly magnetized polar flow initially that then is quenched. The Fishbone-Moncrief one has a more powerful magnetized emission along the pole for a longer time, but it sort of turns on and off and is not very powerful either. And if we look at what's happening at the horizon, so here you see the mass accretion rate, and I'm plotting the twice resolution ones just to see that it's very similar, as well as the normal resolution ones. And you see that the Fishbone-Moncrief torus immediately accretes and then drains. The Chakrabarty one accretes very slowly. And if we measure the magnetic flux on the horizon, it's very bursty for this thick disk case, but gets quite high, whereas it remains very low for the Chakrabarty case. So it's not able to transport magnetic flux to the horizon nearly as efficiently. But even this thick disk case transports it in a way that is variable, very intermittent. Okay. Sorry, I'm going to skip this. In reality, we think that in mergers, you get about a factor of 10 difference between the toroidal component and the poloidal component of the magnetic field. So we're now running simulations. These are actively in progress where we have a mixed field configuration that is 10 times stronger in the toroidal component. And we see clear differences from the purely toroidal ones, but the overall results remain very similar. So you get some bursty accretion where you get some magnetic flux on the horizon for short bursts of time in the thicker disk case, but for the thinner disk case, you still struggle to get sufficient magnetic flux on the horizon to launch a powerful jet. And Chris already showed that one. So I'll just end this section by saying that you may be able to better generate large-scale poloidal flux with some disk solutions than others, in particular this thicker Fishbone-Moncrief one, and that's consistent with what's suggested in the Liska paper. And it doesn't seem like all tori, depending on their initial conditions, can reach this magnetically arrested state eventually, which is consistent with what Chris and Peyton found. And you may get these sort of intermittent jets, and that's to be further explored.
Thanks, Goni. That was great. One of the things that controls the actual initial thickness of the disk left behind in neutron star mergers or neutron star black hole mergers is basically how much mass there is, because that sets the role of neutrino cooling. So do you think there could be an interesting mapping then from the exact properties of the merger to the properties of the jet that results?
Yeah, I think that's definitely true. So, working with Elias Most, he has these numerical relativity simulations of black hole neutron star mergers that form disks, exploring different initial binary parameters, in particular just the spins in this case. And so what we are doing next is remapping directly from these simulations. But I think even like a parametric study where we explore different initial disk masses without doing the full remapping, just to understand how that particular parameter shapes the results that we get, is an interesting direction to go before this step.
Thanks.
Yeah.
A very interesting presentation. This fishbone-Moncrief result, which didn't show oscillations, may well be just a different manifestation of a similar type of dynamo, which is just having different boundary conditions, essentially. So can you, or maybe also other profiles for the effective dynamo coefficients in the disk. So do you have any ideas which of these aspects are the dominant ones between that and the cyclic dynamo solutions?
I'm not sure. So I am looking at like just seeing how the magnetic field, the average magnetic field in the disk grows at early times in the two cases. And the fishbone-Moncrief one does show some exponential growth very early on. I think that it may be that we need like finer resolution at the early times to explore what's actually happening before it starts accreting rapidly. And maybe it is saturating earlier on than the Chakrabarty disk, and that's why we're not seeing this pattern. But I think, yeah, there's more analysis to be done, and similar analysis to what John has done in his paper for comparison to what they find in their disks.
Great, thanks.
Yeah.
Just a quick follow-on question from that. So in the fishbone-Moncrief simulation, where you attempted to measure the butterfly diagram, is the plasma beta still high? I mean, you mentioned the beta, but I didn't catch it.
It drops very quickly. I mean, yeah, we see that it rises at very early times and then drops quite quickly. It doesn't stay high.
So it's magnetically dominated then, or?
Plasma beta gets pretty high, so it's actually...
Oh, it's high.
Yeah.
Sorry, okay.
Yeah, so it's not very magnetically dominated in the midplane from quite early on in the
And yet it still does not show a butterfly diagram, just so I have the facts.
Yeah.
Later it is not.
Yeah.
Yeah, later it is, but not early.
But
it starts with a beta of 10.
But when you were looking for the butterfly diagram, what
well,
is
the butterfly diagram is over time. So it's measured at one radius.
Yes, right.
I don't remember what the value of beta is as a function of radius at that time, but I can, yeah, definitely check that. The azimuthally averaged beta. Yeah.
But then you have the outflow that is more efficient in that case.
Yeah.
Right? Yeah. I think this is completely connected.
And that you didn't have in the oscillatory solution, right?
Yeah, so because I was.
So am I right that in the oscillatory solution you did not have it in outflow?
In the Chakrabarty disk?
Yeah.
Is that, yeah. There's a weak outflow.
Yes.
Yes,
okay.
but not nearly the same.
What do you mean by oscillatory? What oscillates? Oh, okay. And does the magnetic flux polarity oscillate in the jet region?
That's a great question. I don't think so, but I haven't checked for these specific simulations. When we did lower resolution ones and we're looking at the magnetic field lines, it wasn't switching polarity. Yeah.
So just rather speculative on my interpretation. So in the case that the butterfly diagram completely goes away, you do have a stronger and more efficient outflow, right?
Yes.
So this might say something from this, you know, the kill of the dynamo action, the end of the dynamo action, and this could be connected to somehow to that transition of states that Chris, you know, but of course these are very different physical scenarios, because there it's X-ray binaries, and in here you are talking about a collapsar. But I'm just stressing the fact that you have the outflow formation when you kill this small scale dynamo, right?
Yes,
so
that's
maybe
true.
this transition from the large scale coherent magnetic field that goes out with the outflow. But, you know, this is speculation.
Yeah, I mean, I think even though me and Chris are interested in different systems, the sort of simulations that we do are pretty much identical. And that's like across black hole scales, people run the same sort of initial solutions, and the same physics goes into them, obviously with variations like radiation, opacities.
So wonderful talk. I really enjoyed it. Thanks, Goni.
Thank you.
I'm wondering, do you think that there is a relationship between the butterfly diagram kind of being disorganized and the dynamo working, and then when the dynamo is not working, the butterfly diagram becomes organized, or is this just a coincidence?
I think that it is true that having like a more sporadic dynamo diagram or butterfly diagram is characteristic of these thicker disks and generally seen across the board. It's much easier to see clean butterfly diagrams in boxes. So I don't know if it's just complexities of having like these outflows and the like the fishbone Moncrief disk evolving so quickly that you don't get to see that build up over time. Like the Chakrabarty disk is much more stable. So I'm not sure that that's evidence that the dynamo isn't working, or that it's just easier to look at this pattern in that disk. Yeah.
Thank you so much, Helen.
Thank you.